Hello, I'm Matthew. I'm here to talk about the modern physics. The content of this slide will be presented in the order shown in the index. Max Planck and the blackbody radiation will be first. The second thing will be the importance and the info on E=hf. The third thing will be wave-particle duality and double-slit experiment. The fourth one is the photoelectric effects with Einstein explanation of it, and the problem that will prove that it is true. And the fifth one is photons and have momentums, which is Compton's effects, and it will give an equation to show derivation of it. The sixth one is the Broglie wavelength, and the seventh one is Heisenberg uncertainty principle, and the last one is application of modern physics in the real world, which will be looking at microscopes and chip designs. The topic that will be covered in the part 1 of the slides is black bodies. That will be the terms and the definition of the black bodies. The second thing is ultraviolet claustrophobic, which explains the definition of it. And the last one is a Max Planck, the history of the black body and the contribution of Max Planck did to the black bodies. The terms for black body, the definition, an object that absorbs all radiation reaching it, which is known as shadow. Black body radiation. The definition: radiation emitted by an ideal black body. Early theories on black body. At Planck's time, the theory about black body predicts the intensity of radiation is infinite. However, this theory could not be correct. This theory is conflict with the experimental intensity of the curve. Almost all objects can act as an approximate black body. It is hard to see how all objects emit infinite amount of energy. And this have violated the law of conservation of energy by a lot. This is why this theory is claimed as false. And the picture shown in the slides is Max Planck. The history of Max Planck. Planck have used a glowing oven to explain the black body radiation. The oven emitted a range of wavelength and frequency. The largest intensity of the wavelength determined the color of the oven. This is proven by the experiment done prior to Planck's work. And the experiment showed that the intensity curves has the same shape for a wide variety of objects. Max Planck's goal. Max Planck's goal is to explain the black body's intensity fall to zero at both the long and short wavelength, corresponding to low and high frequency, respectively the peak in the middle. Planck's hypothesis. Planck hypothesized that the energy in a black body comes in discrete parcels. Planck believed that each parcel has energy is equal to hFn. H stands for Planck's universal constant, and Fn stands for standing wave frequency. The image provided is the equation that is trying to be explained in this hypothesis slide. Ultraviolet claustrophy. The definition. This disagreement between theories and experiment. The interesting fact about this, the reason behind why it is called ultraviolet claustrophy, is that the predicted infinite intensity is found at high frequency. And high frequency visible light fall at the ultraviolet end of the electromagnetic spectrum. And this is a really interesting fact I found during my research, and this is why I want to present it here. This is break time. You can either pause the video to take a break, or do nothing and it will continue to part 2. Thank you. The topic that will be covered in part 2 of this slide is Albert Einstein, which will be talking about discovery of photons and quantum, and also in depth of photons and quantum. Here we will explain the equation to calculate the energy for one photon, which is E=hf. Discovery of photons. In 1905, Albert Einstein proposed that light should be thought of as a collection of particles, which is known as photon. Photon, or you can call it quantum, is a discrete bundle of energy that is carried by light. It does not have mass, and it does not exhibit interference effects. The image of photon can be seen at the right bottom corner of the slide. Equation for energy for photons. E photon equal hf. That is the equation. This equation is created by Albert Einstein and Planck. Planck have created the variable for h, which is called Planck constant, and f is the frequency of light. H is a constant with the value of 6.63 times 10 to the negative 34 joules per second. This represents the ratio of the light of a single quantum to its frequency. So, why energy of photon equal hf important? So first we'll talk about photoelectric first. So the absorption of light by an electron is like a collision between two particles, a photon and an electron. The photon will carry energy of hf, which the electron will absorb. When this energy is less than the work function, the electron cannot escape the metal. And light intensity does not affect this phenomenon. So we can conclude that hf equal energy of a photon, very important for photoelectric, which is important and significant to quantum mechanics about lights. And the energy of one single photon, and hence the energy gained by a particular electron, depend on the frequency, but not the light intensity. And this is very important. It's not light intensity, but frequency. So this is why energy of a photon is equal to hf is very important. Now we have reached the second break. You can either pause the video to take the break, or continue to part 3. This is optional. The topic that will be covered in part 3 is a lot. It is recommended to take a break. The topic that will be covered in part 3 is double slit experiment. We will talk about the double slit experiment, the history of it, the use of it, the discovery is made of it, and the different interpretation for double slit experiment. Also, we will talk about wave-particle duality. The definition of wave-particle duality: light is a wave-particle duality, and why? Electron is a wave-particle duality, and why? So, the history of the double slit experiment. The double slit experiment is the experiment done by Thomas Young, which is the image shown at the right. That is Thomas Young. This experiment was performed at the very end of 1700s. And this double slit experiment is also known as Young's double slit experiment. And this is used by many famous physicists. Example, there is Albert Einstein, Max Planck, and there will be more that will be introduced later on in this slideshow. So, the steps for setting up a double slit experiment. First, you need two screens placed apart from each other. And a double slit must be added to one of the screens. After, you need to shoot a light through the screen with double slit toward the other screen that will detect light that will be hitting the screen. And from double slit experiment, you see light being split as part and part and part due to interference wave caused by light. And this is the reason why light is a wave. Discovery that is made from the double slit experiment. Double slit experiment discovery include wave can be deferred and particle can be deferred from each other. So, wave will have a constructive interference between light passing through the two slits. Dark fringes are produced at the location where destructive interference occurs. The particle will have no constructive interference or destructive interference occur. And this is how you identify both from others. And the image shown below is a really cool image I found on the internet, which shows perfectly of what a light and particle is. So at the bottom, that's a wave, which can be said as light. At the top is a particle. Wave can be considered both, and this is why I found this image interesting and I will share it to others. Interpreting the double slit experiment. The double slit experiment interpreting. It is hard to understand the result of photons, electron, or any other small particle. The reason for that is the scale of the picture of nature at very small scale differ greatly from the classical picture at large scale. The spots on the screen is determined by wave-like interference behavior. The equation of quantum mechanics makes precise prediction about the result of a double-slit experiment, but it does not provide a clear description of what happened to the photons, electron, or other particles that will pass through the slit and travel to the screen. And this have caused many different interpretations of what happened in the quantum world, and this have still not been confirmed today. Interpreting the double-slit experiment. So, the first one that will be discussed is collapse interpretation. Electrons sometimes behave as a wave and sometimes as a particle. The second interpretation is pilot wave interpretation. The motion of electron depends on a mysterious wave, which is called pilot wave. And pilot waves depend on everything in the universe. The third interpretation is many-world interpretation. The universe split itself to many versions of itself. Electron pass through the left slit is one universe, and the electron pass through the right slit is another universe. The last one is coherent interpretation. It said that certain question does not have answer. For example, what the electron is doing between it from the one screen to the second screen. It doesn't have an answer. And that's the last interpretation. Now we will be talking about the wave-particle duality. The definition. The definition of a wave-particle duality is the property of matter that defines its dual nature of displaying both wave-like and particle-like characteristics. This includes electron, light, and quantum. So, many may think that light is only a wave, but not. It is a wave-particle duality. It has a property of both light and wave. So, the wave property of light is known already. Is that light can form destructive wave and can be seen from both the double-slit experiment or Einstein's equation. So, the particle properties of light is it consists of tiny particle, which is known as photon. And photon is a discrete bundle of energy that's carried by light. The existence of photon was discovered by Albert Einstein, which is known by many others people, and I'm sure that you know Albert Einstein too. So electron is a wave-particle duality too. An interference experiment with electron. The double-slit experiment showed that electron can exhibit interference, a property that classical theories say that is only possible for wave. In 1927, physicists Clinton Davidson and Lester German performed an experiment in which they aimed a beam of electron at a crystal target. The atoms in the target were spaced at regular interval, act as a series of slits for the electrons. And this is known as Davidson's and Germer's experiment. And this have exhibited interference when the wavelength of the electron is similar to the spacing between the atom and the crystal. The diffraction technique used in the Davidson-Germer's experiment is still used today to measure molecular spacing within a crystal. And this is why electron is wave and particle duality. Now we have finished part 3. It's break time. You can choose to either pause the video to take a break or continue to part 4 of the video. Topic cover of part 4. Here we discuss work function, the discovery of photons, the photoelectric effects that is mentioned earlier. We'll be talking about the definition of it and the reason behind of it. And we will end with one problem-solving question about the topic that is covered above. So, the work function. The work function can calculate the minimum energy that is required to remove a single electron from a piece of metal. The equation for it is W is equal to E times delta V. The W stands for the minimum energy required, and the unit is joules. E is the elementary charge, 1.6 times 10 to the negative 19. Delta V is the electric potential difference at which the electron begins to jump across the vacuum space. Discovery of photons. In 1925, Albert Einstein proposed that light should be thought of as a collection of particles. There's two important properties for photons. Photons do not have any mass, and photons exhibit interference effects. This is mentioned earlier, but is repeated to remind the importance of photons. Part 1 of the definition of photoelectric effect. Photoelectric effect, the phenomenon of electron being ejected from a material when it is exposed to electromagnetic radiation. No electron are emitted unless the light frequency is greater than the threshold frequency, which is F0, the minimum frequency at which electrons are ejected from metal. When the frequency is above F0, the kinetic energy of the emitted electron varies linearly with the frequency. Light frequency higher than threshold frequency will cause the electron to exit the metal and will increase the EK, which is kinetic energy of the electron. Definition of photoelectric effect Part 2. Kinetic energy of ejected electron depend on the light frequency, not intensity. And this will repeat again. Kinetic energy of ejected electron depend on the light frequency and not the light intensity. So HF0 is equal to the work, and EK is equal to HF minus the work. The threshold frequency and the photoelectric effect correspond to the photons whose energy is equal to the work function, and EK is also linear proportional to frequency. Problem solving. Energy of photon equal HF. Problem. Determine the photon frequency. Silver is being used in a photoelectric experiment. Calculate the minimum frequency needed to emit an electron. The work function for silver is 7.43 times 10 to the negative 19. So solving. Energy of photon is equal to 7.43 times 10 to the negative 19 joules. F0 is equal to energy of photon divided by Planck constant. F0 is equal to 7.43 times 10 to the negative 19 joules divided by 6.63 times 10 to the negative 34 joules per second after you substitute the energy of photon into the equation. And as a result, you get 1.120666365 times 10 to the negative 15 Hz. So the minimum frequency required to emit an electron is 1.12 times 10 to the 15 Hz. Now it is break time. Pause the video to take a break or continue to part 3. Topic covered in part 5. Compton's effect. Here we will explain Compton's experiment, the definition of Compton's effect, the derivation of Compton's effect, and one problem-solving question about the topic covered above. Compton's experiment, evidence of photons momentum. In 1923, American physicist A.H. Compton, between 1892 to 1962, discovered a phenomenon that provided experimental evidence of the momentum carried by the individual photons. Compton directed a beam of high-energy X-ray photon at a thin metal foil, which showed the effect in which incident X-ray photons lose energy and scatter off a metal foil along a free electron, known as Compton effect. Compton conducted a series of experiments using different metal foil and different beam of X-ray. X-ray have higher energy proton, and the electron is able to absorb only some of this energy. This experiment brought up the conclusion that X-ray photons act like a particle in an elastic collision with an electron in metal. The photon emerged from the collision with lower energy and a different momentum. The electron deflected with the kinetic energy and momentum lost by the proton. In the diagram at the top right show how the experiment looked like for Compton. Definition of Compton's effect. Compton's effect. The elastic scattering of photons by high-energy photons. This effect was found by the Compton X-ray experiment. This experiment had the result of X-ray photons lose energy and scatter off a metal foil along the free electron. This experiment showed that photons also have momentum similar to particle. At the right, you will see a picture of how high energy X-ray is rated. The derivation of Compton's effect. Derivation. So F times wavelength is equal to C. This is the universal wave equation, and it is known that momentum of photon is equal to hf divided by c. So substituting the c for hf as frequency times wavelength into the equation hf divided by c, you get hf divided by f wavelength. So the momentum of the photon is equal to h divided by wavelength after you cancel both frequency from the top and the bottom from the equation. So this will give you the equation of the momentum of the photon is equal to Planck constant divided by wavelength. In this break time, you can either choose to pause the video to take a break or continue to part 6 of the video. Topics that will be covered in part 6 is the Broglie wavelength, the discovery of the Broglie wavelength, definition of it, and the equation of it. And it will have one problem-solving question about the topic covered above. Discovery of the Broglie wavelength. The Broglie wavelength by the early 1920s, physicists were struggling with how to describe particles such as electron in the quantum world. 1924, Louis de Broglie suggests that all classical particles have wave-like properties. Louis de Broglie thought that if a particle have wavelength, the particle should exhibit interference just as waves do. Louis de Broglie established a theory to agree with the behavior of photons. The momentum of photons is equal to h divided by wavelength. So Lewis used this equation to hypothesize that particle with momentum p has a wavelength equal to Planck constant divided by momentum. Definition of the Broglie wavelength. The Broglie wavelength definition: the wavelength associated with the motion of a particle with momentum. The wavelength associated with the motion of particle possesses momentum of magnitude of p. Broglie hypothesis was to look for interference involving classical particles. So important for you to notice, according to Broglie wavelength equation, a long wavelength means that the value for the momentum has to be small. So the particle with very small mass is required, and the lightest known particle at the time was electron. This brought the first observation of matter wave. Matter wave is the wave-like behavior of particle with mass. It is possible to determine the Broglie wavelength for a large object. However, the momentum of large objects tend to be too large that it might imply an extremely small wavelength. Problem solving. The Broglie wavelength of an electron. The problem. In the study of interference with electron, John and Johnny used an electron with a kinetic energy of approximately 55 eV, which is equal to 8 times 10 to the negative 19 joules. And the mass of an electron is 9.11 times 10 to the negative 31 kilogram. So find the Broglie wavelength for these electrons. So solving. So we know the mass of an electron is 9.11 times 10 to the negative 31 kilogram. And the kinetic energy is equal to 8 times 10 to the negative 19 joules. And the Planck constant is equal to 6.63 times 10 to the negative 34. So the kinetic energy is known as half of mv squared. So the velocity is equal to root of 2 times kinetic energy divided by mass. So the velocity after substituting all the numbers is 1.3 times 10 to the root 6 meter per second. The wavelength is equal to Planck constant divided by momentum, which can be written as Planck constant divided by mass times velocity. 6.63 times 10 to the power of negative 34 divided by 9.11 times 10 to the negative 31 times 1.3 times 10 to the root power of 6 after you substitute the numbers in. The wavelength is equal to 5.49 times 10 to the power of 10 Hertz. So the Broglie wavelength is 5.49 times 10 to the power of negative 10 Hertz. Now it's break time. You can pause the video to take a break or continue to part 7. Topic covered, part 7. Werner Heisenberg. We will talk about the discovery of Heisenberg uncertainty principle. Definition of Heisenberg uncertainty principle. The Heisenberg uncertainty principle is a German physicist Werner Heisenberg discovered a limitation on measuring on quantum system. Heisenberg discovered the principle state that there is a limit to how accurate simultaneous measurement of the position and momentum of quantum object can be. The limitation is not easily seen in the macroscopic world, but easily seen in the quantum world. The rules for Heisenberg uncertainty principle. The Heisenberg uncertainty principle is a mathematical statement that says that if delta x is the uncertainty in a particle's position, and delta p is the uncertainty in its momentum. If delta x times delta p is bigger or equal to h divided by 4 pi, then and h is equal to Planck constant. And caution, if you measure momentum with great accuracy, then it will mean little accuracy for the position. And measuring will also disturb the system, although this disturbance is not big in the macroscopic world but huge in the quantum world. The equation is delta x times delta p is bigger or equal to h divided by 4 pi. Example, the width of the slit could cause increase or decrease uncertainty to momentum or a change in position. Break time. You can either pause the video to take a break or continue to part 8 of the video. Topic covered. Part 8. Application of modern physics in the real world. Electron microscope. We'll talk about the history of electron microscope, the function of electron microscope, and then we'll talk about chip design and the aim of the chip design. Electron microscope. Electron microscope is inspired by the Berkeley wavelength. It initiated the study of electron optics. In 1931, the first electron microscope was made. The first electron beam need to be aimed in a vacuum for the electromagnetic lens to detect the image from it. The image results from a scattering of an electron by atom into specimen. It is different from normal microscope that use light absorption to see the specimen. Chip design. Chip design is used in computer and other electronics. The chip aimed to be smaller as it developed to fit in more to smaller objects. It used to run complex programs to perform certain tasks. First, an integrated chip is made in 1958 with the size of 17.76 millimeter square. The modern physics technology made it more compressed and run program better. This is the end of the video. Thank you for watching. Please like and subscribe for the video. Thank you.